Hi guys, this is a classwork video to help get us started talking about electric fields. All right, let's get to it. So, those of us who are in person have been working on making capacitors. In particular, the original capacitor is something called the Leyden jar. The Leyden jar is the original capacitors. Capacitors are excellent because they're all about energy storage. They're used for energy storage. They're used in those power, those wall warts you use to power. You plug into the wall and use to power your devices or charge your cell phone. They're used in radios. They're used in the control of motors. And capacitors are also seen as sort of an alternative to batteries as they store electrical charge, just like batteries do. Batteries use chemical reactions to store charge. Capacitors are all about the location of electrons. All right, so in person, our classmates went ahead and charged capacitor. They put an electric shock on one side of our Leyden jars. And our Leyden jar is just two parallel plates of metal that are not in contact. And so by charging one side of our capacitor, we added electrons, negative charge, to one side. And those electrons pushed on the electrons in the other plate of our capacitor. All right, and so we say that what caused the charge to build up in our capacitor was that by adding a bunch of negative charge to one side, we caused the negatives in the other side to move as far away as possible, and we connected to a large reservoir of neutral charges, so the electrons in the second plate have somewhere to go, and we call that reservoir of neutral ground. Okay, and so capacitors are an excellent introduction to electric fields because they store energy as a result of having a bunch of electrons on one side of a plate and a relative lack of electrons on the other side of the plate. And that occurs as a result of force acting at a distance. All right, and so force acting at a distance, we visualize those forces, non-contact forces, of which we have gravity and electrical force, through the use of force fields. So when we talk about force fields, often we think of video games like Halo, where you have grenades and there's use a force field to protect yourself. Very fancy science fiction movies. Marvel likes to use force fields. Well, force fields in science are a little bit simpler. It's just a way of visualizing forces that act at a distance. So it's gravity, and that's electrical force. The repulsion or attraction between electrons and protons, positive charges, and negative charges. All right, and so an electric force field, as we have in two parallel plates that we call a capacitor, all right, is just a method of visualizing, what is the force interaction, the pushes and pulls between electrons and protons. Okay, and so if we have a simple diagram, visualization of these forces, and we have a plate that's negatively charged on one side, and we have a plate that's relatively positively charged on the other side, we draw arrows pointing from the positive plate to the negative plate. And why is that? Well, it comes down to convention that goes all the way back to Benjamin Franklin. But the way that we actually go about drawing out electric force fields, which we simplify to just call electric fields, is when we have a positive charge, we draw force arrows radiating outwards in all directions. All right, and again, just a visualization of the force that another positive, a test charge, another positive particle would feel if it was placed anywhere near this proton that we're drawing the electrical force diagram, aka electrical force field, of. Okay? And so something that's important to know is that electrical force is very similar to the force of gravity. And so the further away you get from the source of the electrical charge, the source of the electrical force, the smaller the force becomes. And so with electric fields, we draw that as smaller and smaller arrows. All right? But for positive charges, we draw the arrows orienting away from the positive charge. And for negatives, because negatives is the opposite of a positive, we draw those force field arrows. And again, these arrows are showing, what direction in the size of a force that a test charge would feel. Say if we put a positive charge near this negative, the diagram that we're drawing would say that if we put a test charge right here, say a little positive, this positive would be pulled in this direction that the force field diagram, the electric force field, describes. All right. If we put one up here, the arrow would just say, yeah, it's going to go down, straight down towards the negative charge. Okay. So again, what are electric fields? A way of visualizing a non-contact force that we call electrical force. And how do we draw those? Well, we're just drawing arrows that are concentric, or radiating outwards from positive charges. So positives, we have force arrows going outward. Negatives, we have force arrows going inwards. Why do we do that? Because we've defined this based on convention from the 1700s, where we have little test charges, and our test charges are positively charged, and we want to see what direction a positive test charge would move. And if we put a positive near another positive, it should move outwards. If we put a positive near a negative, it should move inwards. All right, so our convention is negatives, the arrows point towards them. Positives, the arrows point away. What are these arrows? They're vectors, which is just a representation of force, a quantity with magnitude and direction. All right, so that brings us to another question, which is we had a quick demo in class where we had a source of electric charge. In this case, this diagram, we have a little bit Tesla coil. And Nikola Tesla, the inventor of this, was, he very much a showman. He liked to light light bulbs, in this instance, a neon light bulb filled with the gas neon. And without any wires, get the light bulb to light in the presence of the source of an electric charge. All right, and so why would that happen? It's bizarre, right? Well, again, we can visualize that using electric force fields. And so what Tesla would do is he'd take this light bulb and he'd move it around his coil, and if he went really far away, the light would become dim and eventually turn off. If he came really close, it would brighten up. And so that's something, that overall phenomenon is something that we can show with electric fields. All right, so say we have a charged object. It's negatively charged on the surface, all right, just like our Van de Graaff generator or Tesla coil. Got a whole bunch of negatives. And so if we want to know how objects around it will interact with that negative charge, we would draw our force field. All right, and so we draw an arrow inwards. Again, these arrows are showing what would happen to a positive charge nearby this object. Okay, what has positive charges? Everything has positive charges, as all atoms are made up of protons, positive charges, and electrons, negative charges. All right, and the further and further away we get from the source of a charge, the smaller we draw our arrows, because these arrows show magnitude, size, and direction. Okay, and so if we're thinking of our lamp as being made up of atoms with positives and negatives surrounding the atom, well, the positives in the atom are pulled towards our negative charge, so we can see with the arrows, and our negatives are repulsed. Okay, but as we can describe electrical force with force fields, why did the light bulb become dimmer the further away we are? Well, electrical force, the further you get away, our force fields have been drawn with smaller and smaller arrows, because electrical force decreases with distance, just like gravity does. All right, So when we say force fields, it sounds like a complicated topic. Really, it's all about electrical force and trying to visualize that with arrows of different size and direction to show electrical force is a non-contact force. All right, that's enough to get us started on this concept. See you guys in class.